Chapter 8, What a Pie. This is the final chapter. Wow, you guys are dedicated. I'm impressed, I truly am. You must really love numbers. Well, I've officially run out of things to share about prime numbers that you can't already find in every other numbers book, at least anything I can think of, so I figure I'm going to do something totally removed from the topic of prime numbers. Let's see how you can tackle pi. Okay, I get it. Pi doesn't seem that challenging to most people. In fact, almost everyone I talk to believes that pi is the simplest math they know, i.e. 22 divided by 7. Well, I hate / love to burst bubbles, people, but everyone who believes pi is a simple division problem is dead wrong. Most people do not realize that pi is what's called a transcendental number. And this simply means that it has an infinite decimal sequence that will never repeat in any consistent pattern. Unfortunately, something like 22 divided by 7 will repeat eventually. Thus, a lot of really smart mathematicians figured out how to calculate pi correctly using a lot of really complicated formulae. Most of which I won't bother to express here because it's over my head. Anyway, pi is probably a lot more complicated than most people will ever know. Google it if you don't believe me. As such, I'm dedicating this chapter to those few open-minded individuals with a love for numbers and a lot of patience with me. Let's just get right into it, shall we? How to create a simple function of pi, just for fun. The following equation for pi, i.e. 4 divided by 8n plus 1 minus 2 divided by 8n plus 4 minus 1 divided by 8n plus 5 minus 1 divided by 8n plus 6, all multiplied by 16 to the power of negative n, was discovered by Simon Plouffe, Peter Borwin, and Jonathan Borwin. You can read the book The Joy of Pi by David Blaitner for more information on this subject, and I strongly suggest that you do. I've determined that the previous equation can also be written as 960 times n to the power of 2 plus 1208 times n plus 376 divided by 4096 times n to the power of 4 plus 8192 times n to the power of 3 plus 5696 times n to the power of 2 plus 1552 times n plus 120, all multiplied by 16 to the power of negative n. Both of these formulae produce the same output for every value of n. The variable n counts from 0 all the way to infinity. Notice how my formula expresses more of an exclusive calculation for the numerator and denominator parts of the intended fraction it represents. Examples. If n equals 0, then the result is 376 divided by 120, multiplied by 16 to the power of 0. If n equals 1, then the result is 2,544 divided by 19656, multiplied by 16 to the power of negative 1. If n equals 2, then the result is 6,632 divided by 157080, multiplied by 16 to the power of negative 2. If n equals 3, then the result is 12640 divided by 609000, multiplied by 16 to the power of negative 3. It's important to understand that the fraction result for each value of n does not in and of itself produce an accurate calculable value of pi. However, when each of these individual fraction results are added together sequentially, you will then get a more approximate value of pi, accurate to at least n divided by 2 plus n plus 1 decimal places. Please note that regular calculators typically will not correctly display these results because they don't have the memory. I personally feel at this point that it's easier to add these together on paper by hand the old-fashioned way, unless of course you're luckier than me and have ready access to a supercomputer that you can easily calculate such things on. Then again, maybe for fun, you could just turn these fractions into infinitely repeating decimals and place them on a chart together, with each row being an ever-increasing value of n. Then maybe you could simply add up the numbers in each column to work out the different decimal digit values of pi. This kind of sounds similar to the hex filtration chart when you put it like that. See example chart number 4a. At this point, I would like to share a different method, which I've personally worked out for deriving these fractions of pi, that I think is far easier to do by hand. I noticed that each result for n was always an ever steadily increasing fraction. I managed to figure out exactly what amount each fraction's individual numerator and denominator amounts increased by to get the next fraction result in the sequence. FYI, please don't be confused. I use a different method to calculate the numerator part of the fraction for any given value of n than the one I used to calculate the denominator with. However, both methods are similar, so it shouldn't be that much of a big deal. Just remember, despite the varying methodology used, each one corresponds to the same specific value of n, just like in the previous example. However, both methods are kind of weird because their result is not actually the numerator/denominator of the value of n being calculated. For example, the calculation of n for both methods gives the corresponding numerator/denominator for the following value of n equals 1. But the calculation of n equals 1 still uses the number derived from the calculation of n equals 0. Confused yet? I thought so. Don't worry, I believe it is simpler than you think. Just try not to forget which fraction calculations are meant to go together for the same value of n. I'm confident you'll do just fine. Finding the numerator. Fortunately, finding the numerator for each separate fraction in the sequence is easy. You only need to know 2 steps along with the number constant of 1920. Okay, I concede that there is one little exception. When n equals 0, the constant is 1792, not 1920. I don't know why, so don't bother asking. Please feel free to verify each numerator however you like, but remember that you can find both numerator and denominator numbers for the first 4 incarnations of n in the previously given examples. Just to simplify things a bit, let's refer to the output value from step 1 of any given calculation of n as a. And let's also refer to the output value from step 2 of any given calculation of n as b. Be ready, I will be referencing the variables a and b in the explanation below. Step 1. Determining the value of a. If n is equal to 0, then simply add the number 1792 to the number 376. If n is not equal to 0, then add the constant 1920 to the value calculated for a of n minus 1. Step 2. Determining the value of b. If n is equal to 0, then simply add the value of a from step 1 to the number 376. If n is not equal to 0, then add the value of a from step 1 to the value calculated for b of n minus 1. Examples. If n equals 0, then a equals 1792 plus 376 equals 2168. And b equals 2168 plus 376 equals 2544. FYI, the number 2544 is the numerator of our fraction for n equals 1, and also is used in step 2 of n equals 1. If n equals 1, then a equals 1920 plus 2168 equals 4088, and b equals 4088 plus 2544 equals 6632. FYI, the number 6632 is the numerator of our fraction for n equals 2, and it's also used in step 2 of n equals 2. If n equals 2, then a equals 1920 plus 4088 equals 6088, and b equals 6088 plus 6632 equals 12640. FYI, the number 12640 is the numerator of our fraction for n equals 3, and it's also used in step 2 of n equals 3. If n equals 3, then a equals 1920 plus 6008 equals 7928, and b equals 7928 plus 12640 equals 20568. FYI, the number 20568 is the numerator of a fraction for n equals 4, and it's also used in step 2 of n equals 4. Okay, just to clarify, if you don't get it yet, look at the above example for n equals 0. Those numbers are not arbitrary. This is all verified via the formula I showed you at the beginning of this chapter. Notice how the value derived from A is used to calculate the value derived from B, i.e. 2168 is used to calculate 2544 in n equals 0. Then the odd part. When next calculating for n equals 1, we use 2168 from n equals 0's calculation of A to determine the value of A in n equals 1, along with the expressed constant of 1920. Then we take the A result of n equals 1 and add it to the B result of n equals 0 to get the numerator of n equals 2. I know, this is super unconventional, but this method works perfectly for every iteration of n. Go ahead, try it yourself, and you'll see. Bizarre or not, it really works. Finding the denominator. Finding the denominator of each fraction is a little more tricky, but when you understand this method, you will find it's effectively as easy as the one used to find the numerator. This method requires 4 steps of addition to work through, and I will show it to you with examples. Please note that n equals 0, n equals 1, and n equals 2, and n equals 3 all have special rules. So for this example, please work with n equals 4. To determine the denominator for n equals 5, i.e. the next fraction in the sequence, you need to know 5 numbers. A constant of 98304, plus 4 additional numbers which are not constant, so don't get confused. These are presented in a very specific order. They are number 1, 294912, number 2, 609408, number 3, 1061328, and number 4, 1670328. Take note that the number 4 value is the denominator of the current fraction of n, which of course in this case is n equals 4. These numbers were derived by my own calculation. I'll show you how a bit later, and they are used to find 4 more numbers to replace the 4 values currently being used. These 4 new values are used to perpetuate the calculations for subsequent iterations of n in the pi fraction sequence, then re-input with the constant. In this case, we will use the numbers associated with n equals 4 to determine the 4 new numbers associated with n equals 5, as well as its denominator. The numbers we derive from this will be used to calculate the denominator of n equals 6 and all 4 numbers associated with it. Here's how it works. Step 1. Let's call it W for no good reason. W equals constant plus number 1. Remember this result as W becomes the new value of number 1 for the next iteration of n step 1 calculation. Step 2. Let's call it X for no good reason. X equals W plus number 2. Remember this result as it becomes the new iteration of number 2 for the next iteration of n's step 2 calculation. Step 3, let's call it y for no good reason. Y equals x plus number 3. Remember this result as y becomes the new value of number 3 for the next iteration of n's step 3 calculation. Step 4, let's call it z for no good reason. Z equals y plus number 4. Remember this result as z becomes the new value of number 4 for the next iteration of n's step 4 calculation, and, FYI, the value of z is the denominator for the current iteration of n that we are calculating. Example, how to find the denominator for n equals 5 following the steps listed above, using the established constant 98304, plus the 4 numbers I already gave you in the first paragraph of this section for n equals 4. Step 1, w equals 98304 plus 294912 equals 393216. Step 2, x equals 393216 plus 609408 equals 1002624. Step 3, y equals 1002624 plus 161328 equals 206392. Step 4, z equals 206392 plus 167038 equals 3734280. The denominator of n equals 5. Now, by simply following the sequence, you can work out the denominator values for each of the subsequent incarnations of n. So, just for good measure, to get the denominator of n equals 6, use the new numbers we just derived from calculating n equals 5 plus the established constant 98304. Step 1, w equals 98304 plus 393216 equals 491520. Step 2, x equals 491520 plus 1002624 equals 1494144. Step 3, y equals 1494144 plus 2063952 equals 3558096. Step 4, z equals 3558096 plus 3734280 equals 7292376, the denominator of n equals 6. Okay, I'm sure that should be enough for a smart bunch like you to figure out how to calculate this stuff. Let me give a quick one over regarding those exceptions I told you about before I finish, though. Exceptions. As promised, but don't expect much. There are only 4 exceptions to the rules with finding denominators. They apply to n equals 0, n equals 1, n equals 2, n equals 3. This is why I started with n equals 4 earlier. Unfortunately, there really is no special shortcut to find the denominator for n equals 0. Just know that it's simply 120, which I got from the formula that this chapter started with. Just remember these work a bit differently. I'm going to leave it up to you to work out those small differences, but don't assume any of those differences affect how the overall denominator pattern works. Try to connect the numbers for each of the next 4 examples from n equals 0 to n equals 3. Now to derive the denominator for n equals 1 from n equals 0. Step 1. Let's call it w again, for no good reason. W equals 19416 plus 120 equals 19536. Step 2. Let's call it w again for no good reason. X equals 19536 plus 120 equals 19656, the denominator of n equals 1. Yeah, that's it. Just 2 steps for this one. To derive the denominator for n equals 2 from n equals 1, use step 1. let's call it W. Okay, I'm sure you get it. W equals 98472 plus 19416 equals 117888. Step 2, let's call it X. Obviously, X equals 117888 plus 19536 equals 137424. Step 3, let's call it Y. Y equals 137424 plus 19656 equals 157080. The denominator of n equals 2. Yes, only 3 steps this time. To derive the denominator for n equals 3 from n equals 2, use step 1. Yes, let's call it W. W equals 98136 plus 98472 equals 196608. Remember this result as W becomes the new value of 1 for the next iteration of n step 1 calculation. Let's call it X. X equals 196608 plus 117888 equals 314496. Remember this result as X becomes the new value of number 2 for the next iteration of n's step 1 calculation. Step 3, let's call it Y. Y equals 314496 plus 137424 equals 451920. Remember this result as Y becomes the new value of number 3 for the next iteration of n's step 1 calculation. Step 4, let's call it Z. Z equals 451920 plus 157080 equals 609000. The denominator of n equals 3. Remember this result as Z becomes the new value of number 4 for the next iteration of n's step 1 calculation. Now, try to use what you have learned to derive the denominator of n equals 4 from n equals 3 on your own. I'll be nice and provide the constant to get you started. Consider this a little test before I close. There you have it. Now you know how to calculate both the numerator and denominator for any given value of n. What now? Well, go and put the data into a chart that I showed you. Calculate pi. Remember that the whole point with all this stuff was to find the numerator and denominator for the fraction associated with each iteration of n and then solve it, multiplied by 16 to the power of negative n. And input the repeating decimal series into a chart. Once that's done sufficiently, you can add together the digits in each column to get a piece of pi. The more columns you calculate, the more accurate the outcome. I think that everyone here can crunch those numbers with no problem now, but I want to make sure of one last thing. I've mentioned a few times now that the fraction created for any given value of n must be multiplied by 16 to the power of negative n. I assume everyone knows what that means, but I suppose it's possible someone might not. So just let me explain that one real quick. 16 raised to the power of negative n, yes, I said negative n. I know it's not well known for most beginners, but a number can be raised to a negative value. All it really means for us is to multiply the denominator by 16 raised to the power of positive n. I figure the reason they write it with a negative n is just to be difficult, but who could say? Anyway, if you don't multiply each denominator correctly, the chart system breaks down and nothing works. Refer to example chart number 4b. The denominator gets extremely big extremely fast, though. This is why I suggest that you do this stuff by hand. The numbers are freaking huge. Seriously, though, don't trust your calculator. If you don't understand what I mean, just divide 2 by 3. Go ahead. It should be a 0.6 repeating. I bet it ends with a 7, doesn't it? And they call that junk accurate. Why do I feel like I need to write another book? Well, anyway, I thank you for spending your time with me. I hope you enjoyed my little book. Until next time, goodbye. I know, not much of a way to end a book, but I'm terrible with goodbyes.